Hey there, we are starting Unit 5 today, and so make sure you get these new notes in. Unit 5 is entitled Inverses and Radical Functions, and with Section 5.1 we're looking at operations with functions. Now a lot of this section today is going to make sense, I hope. The one thing that some students will get caught up on is with division, but I'm going to try to make that as clear as I can with this video. And again, of course, if you have questions, email or hit up that Zoom meeting from 1 to 2. All right, so here we go. The objective of this lesson is that we will be able to perform arithmetic operations with functions and be able to apply arithmetic operations with functions. And so these are the standards that we're looking at is FBF1, being able to describe the relationship between two quantities and dealing with those expressions in different manners. And so let's just review some notation real quick. Obviously, we have our four basic operations: addition, subtraction, multiplication, division. And so when we see these here, like f plus g of x, that means I'm going to take my f function and add it to my g function. For subtraction, same thing. F minus g of x means I'm taking the f function and subtracting it from the g function. Multiplication is the same way. Now, I want you to pay attention what symbol we're using here. We are using a dot here, and it is just a little regular multiplication dot. That's going to be important for what we're going to look at tomorrow. We're going to use a different symbol for a different type of way to combine functions. We're going to call those compositions, but we'll worry about that tomorrow. And finally, division. F divided by g of x means we're taking the f function and dividing by the g function. Remember, the only stipulation is that we cannot divide by 0, and so the g function cannot be just equal to 0. It's got to have something there other than that. All right. So let's take these functions here. I'm going to add and subtract them together to find each function. So we're given the f here, we're given the g here, and in our first problem we're asked this new h of x function is going to be the sum of the f function and the g function. And so I'm literally going to write this, that h of x is equal to 5x squared plus 3x minus 5 plus x squared minus 2x plus 1. Now, it's addition, so I can just drop all the parentheses and combine the like terms. So the x squared term with the x squared term will give me 6x squared. And then we'll take the x term with the x term, and we're doing 3, get the same color here, 3 plus negative 2 is positive 1, so plus x. And then we're going to take the minus 5 and the plus 1, so negative 5 plus positive 1, and so that would give us a negative 4. And so h of x is equal to this function here. And so it's just that simple. Again, it's nothing crazy complicated. It's just adding together our like terms like we've done before. And so the same thing is going to happen with subtraction. Okay, so I'm going to take the same two functions that I had, so I'm going to have to keep the screen up on these functions for a second. But I'm going to have that my h of x, h, is equal to the 5x squared plus the 3x minus the 5 minus this time x squared minus 2x plus 1. Now, dealing with the subtraction here, remember we're going to combine our like terms. And now there's one of two ways we could do this. We could just say 5x squared minus x squared and get our answer. Or we can distribute this negative first. And that's sometimes the more advisable thing so that our signs come out a little bit easier. And so I'm going to rewrite this as h of x is equal to 5x squared plus 3x minus 5. Now distributing the negative to all of these, I'm going to get minus x squared. Negative times negative is going to be a positive 2x. And negative times positive is going to be a minus 1. Now we'll combine those like terms. So the x squared with the x squared, so I get 5x squared minus x squared, and that's going to be 4x squared. We'll do the same for the x term, so we have this plus 3x and plus 2x, and so that's going to give us plus 5x, and then we're going to do the last for these terms, so the minus 5 and then minus 1. So negative 5 minus 1 is negative 6. And so h of x is equal to 4x squared plus 5x minus 6. So again, nothing crazy there. All right. I don't think we're going to do the second example here. Again, it's the same idea. I'm going to skip it for the sake of time for this video. But let's come to this statement here. The domains of functions consist of the x values. Remember, we're talking domain, right? Domain is the x value. So the domain of functions consists of the x values that are in the domain of both of the functions f and g. And again, we could have any two letters here, but we're going to use f and g as our general cases. Also, the domain of the quotient, key thing here, does not include the values for which the denominator is equal to 0. Now this would again be the x values. So again, the domain of the quotient would not include any x values for which will make the denominator equal to 0. Okay, we'll talk about that a little bit more in a minute. First, let's take a little review of some parent functions. And so the first type of function we're going to look at is the constant function. Remember that this is going to be the line y equals 0 because it goes through the y-axis at 0. Right? Now, the general form of any constant function is in the form y equals c, with the c being the y-intercept of that line. Now, let's talk about the domain and the range of a constant function. The domain is really simple. This function goes from negative infinity to positive infinity, right? So the range is all real numbers, or the range is from negative infinity to positive infinity in interval notation, right? The range is a little different. The range of a constant function is only the value itself, the c. So again, if my line were here at positive 5, my range would just be the c. There would be no other value for it. All right. Linear functions, remember that linear functions are going to be lines, right? And those fall in the parent function y equals x, but the general form, of course, is the slope-intercept form y equals mx plus b. Now, let's talk about the domain. Let's talk about the range. The domain of a linear function is all real numbers from negative infinity to positive infinity. And I'm using the interval notation here because I will tell you what we're going to do next is going to be so much easier in interval notation than it will be in any other notation. Now, what's the range? What y values does this graph cover? Again, it is all real numbers, so it is going from negative infinity to positive infinity. Okay? Quadratic functions, remember the parent is y equals x squared, and the general form of a quadratic, the standard form, ax squared plus bx plus c. Now, let's talk about the domain and the range of this quadratic function. Again, the domain is really easy. This graph's going to go on forever in x in both directions, so it's from negative infinity to positive infinity. But the range is going to be dependent on a certain thing here, right? So if we're talking about our parent function, the range starts at 0 and goes to positive infinity. So we could write it as y is greater than or equal to 0, but remember we want to write this in interval notation, and so that's going to be bracket 0, comma, infinity. Okay, go back to section chapter 1 when we did interval notation early on in the year. Okay, now if this parabola were shifted up and down, remember I'm always going to be looking at the vertex, and that will tell me what my range will be. And if this parabola would open down, that would change the side that these are on. Cubic functions, again, the general idea is the same. Y is equal to x cubed is the parent of all cubic functions. Everything is a transformation of that. And the general form of a cubic is ax cubed plus bx squared plus cx plus d. You might see it a sub 3 and a sub 2 and a sub 1 and a sub 0 for the coefficients and the constant. Again, that's just a different labeling system. let's talk about the domain and range of this. And again, this is the important part that I want you to get for what we're going to do next. The domain of this function is all real numbers. It goes from negative infinity to positive infinity. The range will do the same because it's going down to the left, it's going up to the right as we look at this parent function. And it doesn't matter what twists and curves a cubic function has, because remember, your left-in behavior, as long as the a is a positive value, would go down and to the left, and it's going to go up and to the right in the other direction. Now let's look at two functions that we haven't talked a lot about yet, but we're going to talk more about in this chapter. And so the square root function. So the parent function is y equals the square root of x, which we can also express as x to the 1/2 power. Now, the general form of a square root will be in this form. Y is equal to a times the square root of x minus h plus k. And again, you might see it with parentheses with an exponential power, a rational power, instead of with the square root. Either form would be the same. Okay. Now this hk is the starting point of our square root function. And so if this function were starting here and going out this way, my hk would be negative 5, 5, right? And those would plug in here. And the a value deals with the, again, the vertical dilation of this function. And because, again, as we talked back in chapter 2, all of these stay together. So what is the domain of this function? Well, the domain starts at this point. And so my domain is going to be hard bracketed at my h and go to positive infinity. Now, if I'm here, it would be from 0 to infinity, right? And 0 would be bracketed, and the infinity is not. The range would do the same thing. It's going to be hard bracketed with the k and go to positive infinity. Now, if my a were negative and this were opening down, or this were opening to the left instead of to the right, then of course the domain and range is going to switch to accommodate those directions. Finally, the cube root function. The cube root function will look very similar to the square root function, except instead of the 1/2 power, now dealing with the 1/3 power. And so y is equal to the cube root of x, that's this purple line here, or we can write it as x to the 1/3. The general form, again, will look like it did for square roots. Y is equal to a times the cube root of x minus h plus the k, or I could write it with the rational power 1/3. Let's fix that. 1/3 plus k. Now, where is this hk? The hk comes into play where this graph looks like it's going to start turning to go up, right? Or if it's coming the other direction, turning to go down. But then we see it kind of just, oh, I'm going to go back this way. This is the ordered pair of our hk in a cube root function. And so, what is my domain of a cube root function? Well, it goes off to negative infinity, it goes off to positive infinity. So it's all real numbers. And what's the range of a cube root function? Well, it doesn't look like it's growing very fast, but it will continue to grow the further we go out. And so the range is also all real numbers for a cube root function. And so the only function that we have some weird domains and ranges for is the square root function. The domain and range both have a bound to them. And of course, the quadratic function, the range, has a bound to it. Okay? Now, let's look at the rest of these examples here. Talking about multiplying and dividing functions. So I've got the same two functions that I had before. Now, multiplication is going to be really easy here. The division, we're going to talk about what's going to happen. Okay? So given that these are my two functions, let's multiply them together. And so I'm going to get that 5x squared plus 3x minus the 5 times the x squared minus 2x plus 1. Now, sorry, moving my chair there. 5x squared plus 3x minus 5 and x squared minus 2x plus 1. Now, the quickest way to multiply a 3 by 3 three terms in both polynomials. So a trinomial times a trinomial is to set up our boxes. 5x squared plus 3x minus the 5. And again, this is what we did in chapter 2, x squared minus the 2x plus the 1. And we just write out this multiplication. So we're going to get 5x to the 4th. We're going to get 3x to the 3rd. We're going to get minus 5x squared. The next box, negative 10x to the 3rd. Make sure you get your powers right here. It's very easy to confuse them. This will be minus 6x squared. This will be a positive 10x. This last box here is negative 5. This is 3x. And this is 5x squared because we multiplied by a 1. Okay, now we combine our like terms, and so we're going to get 5x to the 4th. We got two x cubed terms here, so minus 7x cubed. We've got 3x squared terms, so I've got a negative 5 and a positive 5. Those will cancel, leaving me with the negative 6x squared. This will give me a positive 13x and minus the 5. Now, this would be our new h of x, because that would be the product of those two functions. Now, the question says indicate any restrictions on the domain. Now, those restrictions come in back with the statement we said before. I go with what I have for both functions. Well, what was the domain of this first function? It's a quadratic, so it's all real numbers. And this is a quadratic, so what's the domain of that one? It's again all real numbers. And so my domain of the h of x is from negative infinity to positive infinity. It's all real numbers because both functions could be all real numbers. Now, let's talk about this f divided by g of x. This one's going to be a little bit different because we've got to write out this division. And so again, want to be able to see what I'm going to write here. So I'm going to get the 5x squared plus 3x minus 5 being divided by the x squared minus 2x plus 1. Now, we're dealing with dividing by a quadratic here. We have not talked about doing long division, so I'm not expecting you to simplify this, okay? What I want you to get from this is what things would not be in our domain. Now, the numerator is a quadratic. Its domain is all real numbers like we just discussed. The denominator, its domain is all real numbers, so everything's fair game. But remember what we said, and we're going to scroll back up in the notes here a little bit. Back up here. If I'm dealing with a quotient, we do not include any x values that will make the denominator equal to 0. Okay, so again, I cannot make the denominator equal to 0. And so I need to know what is going to set x squared minus 2x plus 1 equal to 0, because those will be values that are not in my domain. Now, we could do a couple different methods here to solve this, but if you'll notice, if I do my next puzzle really quickly, 1 is my a times c, and negative 2 is my b, and so I'm going to get negative 1 and negative 1, because negative 1 times negative 1 will give me the 1, and negative 1 plus negative 1 gives me the negative 2. And so this is going to factor to x minus 1 and x minus 1 equals 0. And that just means that x minus 1 is equal to 0, which means x would be equal to 1. So my domain of this function, this new h of x function, would be all real numbers if I wasn't doing division. But because I'm doing division, this value cannot be a part of my domain. And so what that means is I'm going to go from negative infinity to 1, and I'm going to go from 1 to infinity. And notice that I'm using parentheses at 1 and not a bracket here, because I can be as close as I want to 1, but I cannot be what value? 1. Now, what symbol will combine these? This is a union. This is our OR symbol. So my domain is negative infinity to 1 or positive 1 to infinity. So the only value, another way to write our domain would be all real numbers except x not equal to 1, right? So either one of these statements would be the same idea, that 1 is not a part of our domain, everything else is, okay? So as we look at examples B here, again, same idea here. We've got a cubic function here, and we've got a linear function here. And so dealing with those division problems, again, look at your domains, look at what values might not fit. Again, multiplication is going to be very straightforward. The division, let's just talk about the domain of that one real quick. We're not going to do the whole problem, but I want to talk about the domain. As we write this out, it's going to be the 4x cubed, right, over the 6x minus 3. But remember, our domain is going to get restricted by whatever will make the denominator equal to 0. So 6x minus 3 equals 0 means I have that 6x is equal to positive 3, which means that x is equal to 1/2. So that means my domain is all real numbers except x equals positive 1/2 or negative infinity to positive 1/2 union 1/2 to positive infinity. That's it. Okay, so again, those aren't hard problems. Again, the biggest thing is just understanding what values can be a part of my domain and which values cannot be a part of my domain. I'm not worrying about the range here. If I wanted the range, we could go and graph this final function and see where it's going to be. What x values are we going to get out of it? Give you a clue here, though. When I do a cubic divided by a linear, I'm going to end up with a quadratic, right? Because go back to what we did with synthetic division in 4.3. And so we would end up with some quadratic, which means my range is definitely not all real numbers. It's going to get restricted because of what that graph's going to look like in the end. Okay. Example 3, we're just talking about with powers here. Powers aren't going to change anything other than the operations that we're dealing with. And remember that you can only add like terms, right? So if this was a 1/2 power and this was a 1/3 power, would I be able to add or subtract those across? No. Okay. Let's talk about what happens with our first one here. H of x is equal to the 3 times x to the 1/2 plus the negative 5x to the 1/2 power. And these are just square roots. Remember that the 1/2 power is the square root function. Okay, and so we will add the like terms. So 3 plus negative 5 is negative 2x to the 1/2. Our domain here. Is there any value that I cannot plug in for this x? Well, go back to our parent function, right? Our parent function deals with a domain where I cannot plug in a negative value that's going to come out of this radical. Because again, if it doesn't come out real, it's not a proper solution for us. It's a complex solution. And so our domain here is going to be from 0 to infinity, including the 0. It'll have the bracket. Okay, so again, these aren't crazy, but if you follow along, they will make some sense as we go along. I want to talk about C and D real quick because, again, it's going to give us some interesting cases. Subtraction is not an interesting case. You're just going to subtract and be done, right? But let's look at C. So I've got 3x to the 1/2 for the f function and negative 5x to the 1/2 for the g. And so I'm going to get 3x to the 1/2 multiplied by negative 5x to the 1/2. When I multiply the coefficients together, I get negative 15. When I multiply the x's together, x to the 1/2 times x to the 1/2, what do I do with those powers? Remember that when you multiply two powers, you're going to add the powers. So what's the 1/2 plus the 1/2 going to give us? This is going to give us an x. So we end up multiplying two square root functions, and we end up with a linear function. That's crazy. Now, our domain is not all real numbers, because again, our domain is not based on the result, our domain is based on the originals. The original here was at 0 to positive infinity. 0 to positive infinity. So my domain of the final is from 0 to positive infinity. There's nothing we could do to change that. Okay. The f divided by g, again, a very interesting case here. Watch what happens. 3x to the 1/2 over negative 5x to the 1/2. What happens when I divide those? Well, the 3 and the negative 5 aren't going to simplify. That's negative 3/5. But this part, remember what we do with the powers there. We subtract the powers. And so 1/2 minus 1/2 gives me 0. So this is 3 over negative 5, x to the 0, but remember anything to the 0 is just 1. And so our final result here is that this is just negative 3/5. It's a constant function. Now, what's our domain? This is going to get a little more complicated. Because for both these square root functions from 0 to infinity with the 0 included. But remember, this is in a denominator, so I can't have anything that would make it equal to 0. And what would make that equal to 0 is 0 itself. So my domain is not going to be a bracket with the 0, but a parenthesis with the 0 and going on to positive infinity. Again, it's all based on understanding what our original domains were and what is going to result from us plugging in for x to get the denominator equal to 0. All right, last example here, a little bit of a word problem here. We're going to go quickly through it because I know this video is running really long, and I apologize for that, but there's a lot of stuff here that I wanted to make sure y'all got with this lesson. And again, you have the wave week, so make sure you use it wisely. Operations of rational exponent functions. A group of photographers is planning an exhibit for their work. Each photographer will contribute 5 prints to the exhibit, and the cost of the framing, each print will be $7.85. There's also a flat fee of $200 to rent the room for the exhibit. The photographers plan to split the cost. And so what is our cost function going to be? C of x. The cost is this. Each one's going to contribute 5 prints, and each print is $7.85. And how many photographers are there? Well, we don't know that yet, right? So it's going to be the $7.85 times the 5 times the number of photographers. Now, they use the variable x here, so we're going to keep the x as the number of photographers. And so C of x is equal to 39.25, and that will be multiplied by the x. Okay, so we have our C of x. Now, hold on. There's also a flat fee of what? $200. So this is going to be plus 200. There we go. All right, let's go to part B. It says, in addition to the photographers, 3 family members offer to participate in sharing the cost of the exhibit. Write a function P of x to represent the number of people who will pay for the exhibit. Well, our P of x is going to be the number of photographers plus the 3 additional family members. So we get that. And so C says to take our cost and divide it by the number of people who are going to pay for it to get what this represents. Okay, and so we're going to get our C function was the 39.25 x plus the 200 divided by the x plus 3, right? Because again, that's how we're going to divide this out. And this is our C of P of x function. Now, if there are 8 photographers, how much does each photographer contribute to the exhibit? And so where are we going to plug in 8? For everywhere we see x. And so our C divided by P, our cost divided by the number of people paying for it, plugging in 8, I'm going to get the 39.25 times the 8 plus the 200 over 8 plus 3. And so that's going to give us 514 when we combine all this together over 11. And dividing that, 514 divided by 11 is going to give us $46.72 and then 72 repeating cents. And so really we're going to round that up to $46.73. Okay. Now, there is no part E to this, but that would be the final contribution, right? How much does each photographer contribute? They'll contribute $46.73. That would also include how much each family member is going to contribute, right? Because they're also going to split the cost with them, because that's what they said in part B. All right, so that is today's lesson. Again, I know it went really long. I will hope to keep the rest of this week a little bit shorter. But the word of the day is domain. Again, the word of the day is domain. Again, if you have questions about this assignment or this lesson, please hit me up on the Zoom meeting from 1 to 2, or check out the email and email me anytime to let me know what you need. Again, I hope y'all have a great day and stay safe.